start registering again. So the idea is that I provided you with a notebook that is available in the main repository of the course. In this notebook, I'm going to introduce you specific concepts of the Hugging Face library, transformers. So I want to start with the introduction of the pipelines. So the transformers library is actually a complete framework. You can use the transformers library to train your deep learning model, your language model, but you can also use models such as BERT and other models that are available on the Hugging Face Hub to run the inference. So without even training the model, you can use pre-trained model to perform such tasks. So here you have an example of some inferences that they have done. So you can instantiate pipelines. You have the references to the documentation on the notebook. If you open up the link that you have here, you have a list of the pipelines that you can use. You have done only a few tasks in the natural language processing world, but actually you can imagine even other pipelines that are available. You are going to cover other tasks during the course. For example, you have the translation pipeline, you have the summarization pipeline, but you even have the classification pipeline. So, for example, if you want to classify a text as belonging to one specific class, and this is actually will be done during the today's lab. So, for example, here I instantiate a pipeline. So for sentiment analysis. So it's an encoder-only model. It means that you have a model that is actually encoding your text and is predicting a class, is not generating any new text. So here you can simply instantiate your pipeline, and you can run your pipeline over some text. Here I put some sentences. So, for example, I like deep NLP course. I don't like deep NLP course. And in both cases, I predicted a label. In this case, because the pipeline is the sentiment analysis pipeline, the pipeline will take in charge the instantiation of a specific model. In this case, you can see here that if you don't specify any model, your model will be the default one, that is distinct BERT-based uncased, fine-tuned on some dataset for English. And so you have the predicted labels here that are positive for the first one, I like deep NLP course, and negative for the second one, so I don't like deep NLP course. You can also provide an identifier for a specific model. So here you have a specific model running on tweets. So you have BERT tweets-based sentiment analysis. You can find any model you want on the Hugging Face Hub. You have a lot of models. You can instantiate your model, and you can run it through the sentiment analyzer. In this case, that is the name of the variable containing the pipeline, and you can predict the labels associated. So here you have TLDR, the movie was amazing, and this is the positive score with a very high confidence. And then you have what a mess, the plot was awful, and this is negative sentiment with a very high, of course, confidence. So you have the output is a label and a score that gives you the confidence that the model has, the probability that that sentence belongs to the predicted class. So you have 98% for the positive class. Okay. The same idea can be applied to other kind of pipelines. So here, for example, you have a text generation pipeline that uses decoder-only models. It means GPT-like models. So you have only the decoder. You condition the decoder to predict the continuation of the sentence you give him. Actually. And so in this case, you have the default model that is GPT-2, and here you have the generated text. So if I run it with the meaning of life is, it predicts a variable containing the generated text, and the generated text in this case is the meaning of life is to not only be lived in the body, but also to be lived in the spirit of reason, so on and so forth. So I don't assure that this is actually true, but this is what the model predicts. So similarly to the previous case, you can do it. So text generation with a specific model. In this case, I run it with the GPT-2 small Italian model. So it's the Italian model. And if I run it with the prefix il senso della vita è, that is the same of the meaning of life is in English, I predict senso della vita, il fondamento dell'esistenza dell'individuo, and so on and so forth. So you have the prediction of the model with the predicted sentence, actually the predicted text. Okay. So finally, you can also have pipelines with encoder-decoder models. It means that you have models that are able to predict text, generate text, actually having as input another text. It's the case of machine translation, for example, but you have also the case of summarization. So if you give to the model an abstract, for example, for a paper, you can extract a summary of that abstract. So if I run it with scientific articles, can be annotated with short sentences called highlights and so on and so forth. The model is able to understand this text. It's actually very long. It doesn't seem, I cannot go on the right, but it's very long, and it actually predicts a subset, like a summary of the text provided in inputs. And so you have, as a result, the summary text for the inputs. Similarly, you can instantiate your own model here, and you can run it over the same text. Here you can see the difference between different models, because here I give to the model, to the pipeline actually, the same text, but in the first case I predict a kind of a summary. In the second case, this summary is similar to a title. So efficient regression models for scientific articles, it's actually very accurate, but it's not a summary like text, but it's actually similarly to a title. So it means that the model has been fine-tuned to predict the title given the abstract. But actually, the idea behind the pipeline is very similar. The only thing that changes is the model. Okay, now I want to introduce you something that can be very not difficult to understand, but actually can be in your project, but even to understand during the course. That is the concept behind tokenizers. So tokenizers are paired with the model. It means that you have a tokenizer associated with a given model. They come together because the tokenizer learns how to convert text into tokens. And actually we can see during this little overview that it maps the text into IDs that are the entries to get the embeddings for a given token. And actually, because the split is performed in a specific way and the ID is performed in a specific way, if you change the tokenizer in a given model that is already pre-trained, you change almost everything. Because if the model expects the article, for example, being at ID 2, and instead in ID 2 you have another completely different word, you will actually lose all the training that you have done. So tokenizer and the model comes together. So they are paired because they are together. So what I want to introduce you is the fact that you can instantiate a given tokenizer by just calling those two lines of code. So you can import the class auto-tokenizer. Here, just a quick reference. If you have auto at the beginning of the class name, it's actually the library that take in charge the fact that this tokenizer is for a BERT model. So you instantiate by giving the model ID, and it actually instantiates a specific class of the tokenizer that is BERT tokenizer, because different models can have different tokenizers of different kind. I mean, different idea behind the creation of the tokenizer, so how to split words and so on and so forth. But if you use this auto tokenizer class, you can instantiate your tokenizer by just calling this line of code. So you have your tokenizer called by autotokenizer.fromPretrained, because it's already created by the creator of the model. And so you instantiate a tokenizer for the BERT-based cased model. So in this case, it's BERT. The dimension of BERT is base, means that you have a specific number of layers for the encoder. And you have the cased version, means that it makes a difference between capitalized letters and lowercase letters. What I want to show you is the output of the tokenizer. If you run the tokenizer over a given text, so you just call tokenizer and then give him it's a sentence, it gives you the input IDs that are actually the mapping between the text itself, the token that are found in the text, and the ID in the ID, sorry, in the embedding matrix that has been created with the model. So you have also token type IDs. We will see why it's interesting. And you have an attention mask that gives you it's a binary mask. It's 1 for the tokens that are actually part of the sentence, and is 0 for other sentences, for other tokens. What are those tokens? So if you have a tokenizer and you want to train a model, in the batch, during training, the model should have all the sentences that have the same dimensions. It means that you have a sentence of 4 words and other sentences of 16 words, for example, tokens in this case. You want to pad the shorter text to have a length that is equal to the longest one, for example. So because of this, you can specify some parameters to the model. You can, for example, specify the max length. That is the max length that you want to reach. So, for example, if you have sentences that are longer than the max length, the tokenizer will take in charge the truncation of these sentences. So you have even truncation. You want to enable truncation if you want to truncate this, and you have also padding, for example, that enable padding if you want to pad the text to reach the max length. So here you have an example. I set as max length 16, and I said to the tokenizer, I want to pad the sentence to reach the max length. So here I am learning DeepNLP that is less than 16 tokens. So I have the input IDs corresponding to the words, but I even have some zeros that corresponds to the padding. Here in the attention mask, you can see that you have 1 for the tokens that are actually part of the sentence itself, and you have 0 for the padding. It means that the model should not pay attention to those tokens because they are padding. They are not meaningful words. And so here you have even other examples for this. For the first one, I'm learning DeepNLP at Politecnico di Torino. I am a second year master student. I set a max length of 16, but you can see that the model can have, I actually can go on the right, but if you see, in this case, the truncation is not applied because I didn't set any truncation here. So the model predicts the input IDs till the end, so it does not truncate to 16. But if I set the truncation to max length, in this case it's set to max length, I will have, you see here, I input IDs that reach 16, and then the closing token that is actually a separator token and then stops. So all the other tokens are removed. So if I augment, like increase this to 32, I have the full list with some padding because it's less than 32. And I have the attention mask that comes together with this logic of padding and truncation. Yeah, the tokenizers have special tokens. So some special tokens are the CLS token that we have seen during the theoretical lessons together. So this is a special token that is used to encode the beginning of the sentence, but you even have the separator token that is actually used to encode the end of the sentence, or actually if you are doing question answering, for example, you want to separate the question from the context, you can use the separator token. This is a separator token. And so here you can see it in action. If the tokenizer encodes the text to some IDs, but it actually does also the reverse. So it decodes the input IDs to generate again the text. So here, if I decode the input IDs that I had before, I'm learning different P and so on and so forth, and I have also the special tokens. So here I have CLS and separator with padding. So these are the tokens that are automatically inserted when I run it with a max length and padding equal to max length in this case. So I enable padding. The CLS and separator token, they are actually added by default. It means that you always have those two tokens. Yes, just a quick reminder here. If you want to skip special tokens, you actually need to set skip special tokens to true. Perhaps I run this with false and I already have the output, but if you run it with true, it means that those special tokens are removed. It means that if you run this cell, you are not having this kind of output, but you will have only the text without the special tokens. Okay, do you have questions here on the classroom? On the yeah. The input IDs are the index of the yeah, the question is the input IDs are the index of the tokens. Yes, these are the index of the tokens to get the embedding. So you imagine you have an embedding matrix with a lot of rows. Those rows are one for each token in the vocabulary, and these are the IDs to get the embedding. So I access this row to get the embedding of that token. Yes, any other question, even online? No questions? By the way, are you able to hear me online? Like you, because I have an external microphone, so I don't know if you're able to hear me correctly. I hope so. I don't find any feedback on the chat. Okay. Okay, so we have seen how tokenizer works. Of course, the best part of these models are actually the models. So I already said you that the tokenizers are paired with the model itself. You can use the same approach to instantiate a given model. So you can instantiate a given model by calling the AutoModel class. It's a class that automatically infers what is the kind, what is the task for the model that you're going to instantiate. And so in this case, if you have form transformers import AutoModel for sequence classification, you will instantiate a model for sequence classification. And the auto here means that it automatically infers if it's a BERT model, or if it's a Roberta model, or if it's another kind of model. So here, these are the lines that you can use to instantiate a model. So from transformers, import auto model for sequence classification. In this case, it's for sequence classification. So I instantiate a model for a specific task. And I use the same approach. So auto model for sequence classification dot from pre-trained, and then the tag of the model I want to instantiate. In this case, it's BERT. If I run this cell, I will have actually a warning that tells me that this model is actually a model that actually I am instantiating this model from the backbone. The backbone means that this is the model that has been pre-trained, but during pre-training you have no specific task to do. So it means that the model is only the backbone. You have not the linear layer that is trained to perform the classification task. So this is the warning that I have here. So here, pre-trained BERT model is not fine-tuning for any specific task. This is the reason behind this warning. And if you want to use this kind of model, you first need to fine-tune it using some kind of data, or you need to switch to another model that is already fine-tuned for the task. So here, I change the model. So I instantiate an auto model for sequence classification that is actually fine-tuned to do financial classification, sentiment classification. So I have this FinBERT model. So I instantiate this model, BERT model for sequence classification. I actually here have an example for a sentence, a list of sentences. I need first to tokenize those sentences. It means that I run the tokenizer through the model, and I obtained the input IDs, attention mask, and so on and so forth. I can pass this variable directly through the model to run the inference. And so in this case, I have my predictions. And so here I have the predictions from the model. And in this case, the model has been pre-trained with 3 different classes, so negative, neutral, and positive. And here I have actually the logits for the classes, and if I do the argmax, I have the class corresponding to the real prediction. So here I have the max for these 3 elements is the last one. So the element at index 2 and 2 is the predictions. If I have the mapping between the classes and the IDs, I can actually have a readable class. So in this case, it would be positive because Google stocks went up suddenly and they earned $30 billion. So that's actually very good. So it would be a good predictions. Okay. So this is to run inference through the model. It's similar to what the pipelines do under the hood during the running of the pipelines. You can also fine-tune a pre-trained model. Of course, you want to do this because if you have your data, you want to fine-tune your model to perform a specific task. And in this case, the Transformers library have a trainer class. This is a 9-level class that is used to train and evaluate models. You have the trainer API. Please check it if you want to fine-tune a model during the project, for example, or if you want to fine-tune the model during the labs. So here I have a toy model. So this is a toy dataset. Sorry, this is a dataset containing coronavirus tweets divided into train and test. I use the training. Actually, I split the training sentences into eval and train. I compute the labels. So I do a little bit of pre-processing here. And I have, for example, here I have 30,000, almost 51,000 elements for the training set, 1,600 for the evaluation set, and almost 3,000 for the test set. how can I run this fine-tuning? So here I instantiate the model. For example, here I have the tokenizer, the model. What I need to do first, I need to run the tokenization. So because I want to have something that is readable by the model, so I run the tokenization for the training sentences, the test sentences, and the evaluation sentences, and I have all the variables here containing all the information I need. I also here instantiate a label encoder just to have a mapping between the text of the labels and some identifiers, so some numbers identifying the cells. But this is actually some additional code that you don't actually need. It means you just need to have something that maps your labels to some IDs. You can do it with your, as you wish, actually. You can use whatever you want. Here you have, yes, I map all the labels using this label encoding. And here I have actually a specific class that I will create to wrap the dataset. A class that you can use is actually actually a child class of the dataset class from PyTorch. So you can mimic this kind of structure. You have a class that derives from the dataset class from PyTorch, and you have an init function, a getItem function, and a length function. In the init function, you give to the class all the information it needs. So in this case, the encodings got by the tokenizer, sorry. The labels, that are the labels that the model needs to use for the fine-tuning. And in the getItem, you have these kind of parameters. So you have, of course, self, but you have an index. And this index is actually what you use to get a specific encoding and a specific label and return it to the model. It means that this kind of structure is the default one for the dataset, and when the model gets want to get new data during training, it calls the getItem function. It's similar to calling, I don't know, list open square parenthesis 0. It means that the getItem will be called with the index 0. So this is what the list does when you access a specific index. Okay, and so here you have here the length function. It's actually the function that gives you the length of the dataset. In this case, you can put like the length of self.labels. Yes, that is actually the length of the dataset, because those two have the same length. So you can put one of the two. So you instantiate your training dataset, evaluation dataset, and test dataset using this kind of structure. And here you define some additional metrics that you want to measure during the training. So you have, for example, the accuracy, the F1. So you compute specific metrics that you want to monitor during the training. And if I actually go down, yeah, you have this compute metrics function that we can use then, like after. Please be aware of the fact that here you have a dictionary having as key the name of the metric and as value a specific score that you want to monitor. So you have some training arguments that encodes the information on the number of epochs you want to do, the strategy you want to use during evaluation. So if you want to evaluate at each epoch, the save strategy, when you want to save the model, if you want to load the best model at the end, which is the batch size for the training or for the evaluation, the number of epochs here, the output directory where the checkpoints will be stored, and so on and so forth. So you have these training arguments, and then you have the trainer itself that takes those arguments, the model, the training set, the evaluation set, and the compute metrics that is actually the function that we defined that monitors some specific metrics, and I can just run the training by running this. And if I run this, I have this kind of output. The training goes on, and I have at each epoch the specific metrics that I specified here. So the accuracy, F1 macro, and F1 weighted, that are actually reported here. And I also have, by default, the training loss and the validation loss. Okay, I run the training. I can use the trainer itself to predict the labels for another test, another data set. In this case, I want to evaluate over the test set, so I predict the labels over the test set. Here I have all the prediction arrays. It means that I have multiple labels, and in this case, I have the logits associated to all the labels, and but also have the label IDs that are the ones that are the ground truth. And I can use this after to compute my metrics, or I can see the metrics here. You can see the test F1 weight, test F1 macro, and so on and so forth. If you want to deep more into the details, for example, for the project, you can see some notebooks provided by Hugging Face itself that show you some examples for PyTorch or TensorFlow. You can even use TensorFlow, but I suggest you to use PyTorch because it's better integrated in the library. Okay, I want to conclude with a little overview of the of two additional libraries. One is datasets. The second one is evaluate. So those two libraries are separate libraries from the original Transformers one, but they are used to download datasets that you can use also to instantiate some evaluation metrics that you want to use during training, for example, or to evaluate your models. Here I just installed a little bit of things here. Yes, the idea is that if you want to evaluate something, you can import a specific metric. So if I import evaluate, I instantiate the accuracy metric, and here I have just the prediction that are got by running the argmax over the predictions that I had in the preds. So here, from this one, I have these predictions, and I got the argmax to get the class. So here I got just the number corresponding to the class, and I can compute the accuracy by just running accuracy.compute predictions preferences, and just I just compare the two, and I have my accuracy score. For the datasets, it's very easy to download and use datasets. So I can just run from datasets import load datasets. This is a function that is used to load datasets from the Hugging Face datasets hub. So it's similarly to the model hub. I have the datasets hub. So here I have different datasets. Those datasets can be filtered by language, for example. I can choose English. I can choose text classification, for example, and even I can choose a specific task. So if I choose these two, I can go, for example, Yelp review full. It contains review from Yelp, that is a website. So I have here the text of the review and the label here. And they actually can very handy. It's very handy to use the datasets by using these datasets field library. Sorry. So here I can download and load a dataset by just calling the name of the dataset. So here I have this SciTLDR. This is a specific dataset for text summarization in the scientific domain. So I can load my dataset. Here I have an example. I have the source field that contains the text, and then I have the source labels. So which are the sentences that are classified as belonging to the summary, So I have different fields that I can explore depending on the dataset I'm using at the moment. So here I have an example for the preprocessing of those kind of sentences. So I have preprocessing functions that take the inputs, and this is corresponding to the source field in the dataset, take the targets, and actually run the tokenizer to have the model inputs and the labels. So this function is very handy if you want to preprocess all the datasets at once and then use it. And so you don't want to do the preprocessing step each time. So here I use the map function that takes as input this function here, this preprocess function, and actually run the function over all the examples of the dataset. So it's very handy if you want to do all the preprocessing at once. And if you run now an example from the dataset, you can see that you have these input IDs and the attention mask that comes from the fact that I had this additional data by running the tokenizer. Okay, I think that's almost it. Yes, I can filter some columns. So for example, if I want to remove some columns because I don't need them anymore, so I don't need, for example, the source text because it's actually taking a little bit of RAM, I can set the format for the dataset, and I can set only the columns that I want to maintain on the dataset. So I can free up a little bit of space. And here I have then the dataset without the additional text that I removed. I only have input IDs, labels, and attention mask. So here you can see that I have input IDs, attention mask, and labels. Okay, I think that's all. Do you have questions about this? Online, there is some question. Okay, I will be around for the lab. Actually, the lab for today is about name identity recognition and indent detection. So in the first, this is divided into two parts. The first part is for name identity recognition. So you want to identify the entities in a given text. And in the second part, you will have instead something related to intent classification. So you want to perform classification of a given sentence for detecting the intent. So this is an example of the the name identity recognition task. You have a sentence, you identify some of the words as referring to a specific person, so a specific entity. So for example, here you have Albert Einstein, that is a person, German, that is a place, heat, yeah, you have also the action here, frying pan, that is actually a cooking tool, and so on and so forth. So please read carefully the all the instructions for the lab. In the first part, you need to explore the NER task using actually pre-trained models that are available on spaCy and Hugging Face, and you after are asked to evaluate spaCy model and Hugging Face model. So you have a little bit of code that is already done for data preparation. Please make sure that you understand how data are preprocessed, because I already provide you with some code that preprocess data, because I don't want you to spend a lot of time by preprocessing your data. But please be careful and check the output at each cell to understand which is the output that is the format of those kind of variables. And actually, the real code starts with question number 2, where you are asked to predict the named entities by using spaCy, and then evaluate it by using a specific specific package that is called eval for NER. So I actually you actually have all the instructions in the notebook. So if you don't have any specific questions, no, okay. So have a good lab. I will be around for the questions. I leave the registration, actually the virtual classroom up if you have questions online, but I will stop the recording now.